I'm Bilal, and I'll be talking about fairness in classification. And this is a joint work with Isabel, my co-advisors Manuel and Krishna, and Adrian Weller. So if you look at fairness in classification, most of the existing notions of fairness are inspired by anti-discrimination legislation. And these notions are rooted in social sciences and legal ideas of parity or equality. For example, two of the main notions of fairness in classification are parity in treatment and parity in impact. Where parity in treatment or avoiding disparate treatment requires that the classification outcomes should not depend on the sensitive group membership. For example, if we have two data points and they are same across all the features except for, let's say, their gender, then their outcome should not change. And parity in impact or avoiding disparate impact, on the other hand, requires that similar fraction of beneficial outcomes should be received by different social groups. And the beneficial outcomes here, depending on the application scenario, could be being granted a loan and so on. And there's been quite a bit of work on training classifiers that adhere to one or both of these notions of fairness. However, it turns out that parity can actually be a very stringent criterion. For example, there are some well-known impossibility results about parity-based fairness, which state that certain parities cannot be achieved together. And then there is this issue of high cost of parity fairness or tragedy of parity fairness, which states that there are some inherent trade-offs between our classification accuracy and fairness, and insisting on parity-based fairness might lead to scenarios with drastic drops in classification accuracy. And finally, insisting on parity might lead us to situations where all the groups involved might end up losing. For example, if we insist on parity-based fairness, we might have a situation where benefits for all the groups actually decrease. And to avoid some of these problems, in this paper, what we tried to do was we tried to go beyond these parity-based notions of fairness, and we tried to explore some preference-based notions of fairness. And these notions are inspired by fair division literature in economics. And what we'll try to do is we'll try to go from the existing notion of parity treatment to preferred treatment, and we'll try to go from parity impact to preferred impact. And the idea here would be that our outcomes might not follow parity, but all the groups involved would prefer their respective outcomes. And our hope would be that this might lead to some gains in accuracy over parity-based fairness. So what I'll try to do in this talk is first we'll try to define and formalize these new preference-based fairness notions, and then we'll try to train classifiers that adhere to these preference-based fairness notions. So before we define these preference-based notions, let's quickly get some preliminaries out of the way. So I'll be assuming some sensitive features. Sensitive features are some socially salient features like gender and race. We'll be assuming groups based on these sensitive features. For example, the groups could be men, women, African Americans, whites, or any combination of these, actually. So whenever I say group in this talk, I mean one of these sensitive feature groups. We'll be assuming some two classification outcomes. One is a beneficial outcome. I'll call it the positive class, and the other is a non-beneficial outcome. And then finally, we'll be assuming this notion of group preference, where given the choice between many different classifiers, a group would choose the classifier which grants most beneficial outcomes to the members of this group. For example, if we have a group and they have a choice to choose from three different classifiers, classifiers 1, 2, 3, where classifier 1 gives beneficial outcomes to 10% of the people in the group, and classifier 2 and 3 give beneficial outcomes to 30 and 15% of people in the group, then the group will, of course, pick classifier 2. So now let's quickly revisit the existing notion of parity treatment, which is inspired by, again, anti-discrimination notion of parity. And parity here requires that if we have two groups, G1 and G2, then the individuals in group G1 should get exactly the same decisions, even if they were posing as members of group G2. So this essentially means that changing the sensitive feature value should not change the decision that a group is getting. And since we insisted that we cannot use the sensitive feature information in classification, this means that we cannot build group conditional classifiers. That is, we cannot build classifiers like for each of the groups. So let me give you an example of a parity treatment classifier. So let's say we have this data set. And the green box here is the positive class, the red box is the negative class. And what we have is we have men and women. For example, in this box, we have 100 men. In this box, we have 200 women that belong to the positive class. And here we have 200 men, 100 women that belong to the negative class. One thing I would like you to note here is that the feature distribution for men and women is different. So now we want to train a classifier on this data set that adheres to parity treatment. And the optimal classifier that we can train here is this one. And it achieves 83% accuracy. It misclassifies these 100 men. And here we insisted that we should have just one classifier for both the groups. Okay. Now let's quickly get to the new notion of preferred treatment. And this notion is inspired by a fair division notion of group envy-freeness, where envy-freeness essentially requires that G1 would collectively not prefer to be posing as G2. That is, changing the sensitive feature should not increase the group benefits. So this notion here, preferred treatment, it allows us to build a group conditional classifier as long as they adhere to this envy-freeness condition. So let me give you an example of a preferred treatment classifier on the same data set. So we built two classifiers, one for each group. First thing I would like you to notice is that they achieve perfect accuracy. And the solid line here is the classifier for women. Dotted line is the classifier for men. And let's look at both of these classifiers. So when men, they use their own classifier, this one, 33% of them get beneficial outcomes. But if men insist on using women's classifier, which is this one, none of them get the beneficial outcome. So men have an incentive to use their own classifier. And we have a similar situation for women. When they use their own classifier, they get 66% of beneficial outcomes. When they use men's classifier, none of them get beneficial outcomes. So essentially here, both of the groups, they don't have any incentive to change their group. And in this sense, we can say that this classifier, this group conditional classifier, is avoiding reverse discrimination or lowering the bar, where one group would think that only if they were posing as the other group, more of them would get the beneficial outcome. So now let me quickly revisit the definition of parity treatment and preferred treatment. So parity treatment, the existing notion, it required that changing the sensitive feature should not change the group benefits. Whereas preferred treatment requires that changing the sensitive feature should not increase the group benefits. So essentially, every solution that is a parity treatment solution is also a preferred treatment solution. So preferred treatment is essentially, it's a relaxation of parity treatment. And this relaxation is what is allowing us to build a more accurate solution. Okay, so let's quickly get to the existing notion of parity impact, which again is inspired by this anti-discrimination notion of parity. And parity here essentially means that given two groups, G1 and G2, if 20% of people from G1 are getting accepted for beneficial outcomes, then 20% of people from G2 should also be accepted for beneficial outcomes. So what it requires is that all groups should get equal fraction of beneficial outcomes. And let's try to build a parity impact classifier on the data set that we have. So this is the optimal parity impact classifier that we could build on this data set. Here 22% of the men are getting beneficial outcomes and 22% of women are getting beneficial outcomes. On the other hand, this our new proposed preferred impact notion, which is inspired by fair division notion of bargaining problem. And let me quickly explain the bargaining problem here. So we have two groups. Both the groups are trying to maximize their benefits. And whatever solution they have, both of them have to agree on it. If they don't agree on the solution, they will have to fall back to some default solution. And we'll be assuming that that default solution here is the parity impact solution. So let's look at the solution of the bargaining problem here. So group 1, 25% of people from group 1 are getting beneficial outcomes, which is more than what they were getting in parity impact. 40% of people from G2 are getting beneficial outcomes, which again is more than what they were getting in parity impact. So essentially, preferred impact notion requires that all the groups should get at least as much benefits as parity impact. And if they cannot agree on such a solution, they can always revert back to parity impact. So let's build a preferred impact classifier on the data set that we had. And that classifier would be, again, this one. It has a 100% accuracy. We have 33% of the men who are getting beneficial outcomes, which is more than what they were getting in parity impact. We have 66% of women who are getting beneficial outcomes, which is again more than what they had in parity impact. So in a sense, both groups are doing better than what they were doing under parity impact. So neither of the groups has any incentive to go back to parity impact solution. And again, we have an accuracy which is more than what we had under parity impact. So let me quickly revisit the definition of parity impact and preferred impact. So parity impact required that all groups should get similar fraction of beneficial outcomes, whereas preferred impact requires that all groups should get at least as much benefits as they were getting under parity impact. So essentially, every parity impact solution is also a preferred impact solution. And again, preferred impact is just a relaxation of parity impact. And this relaxation is what is allowing us to build more accurate solutions. So let's try to formalize these two preference-based fairness notions. So again, I'll be assuming so that we have a sensitive feature group, Z. We have a classifier, I'll just call it theta, which gives two sorts of outcomes. -1 is the non-beneficial outcome, +1 is the beneficial outcome. So then we can say that the beneficial outcomes that a group Z gets from classifier theta is just the probability that the classifier will give this group a +1 outcome. So given this information, I can specialize this for two groups, men and women, let's say. And so we can say that the benefits that men get from classifier theta is the probability that classifier theta gives, again, a +1 outcome to men, and we can do the same thing for women. So now our preferred treatment classifier would be a classifier under which men get more beneficial outcomes by using their classifier than they would be getting by using women's classifier. And we can have the same condition here for women. So this is how we can formalize preferred treatment. Now let's try to formalize preferred impact. So we'll be assuming that we have two classifiers for men and women. These are the parity impact classifiers. Then preferred impact can be formalized as a classifier which gives more beneficial outcomes to men than they were receiving under parity impact, and gives more beneficial outcomes to women that they were receiving under parity impact. So now let's quickly try to train classifiers that adhere to these two notions of fairness. So generally, when we try to train convex boundary-based classifiers, what we try to do is, given some training data set, we try to minimize some sort of loss, and that loss is convex. So this means that we can learn these classifiers in an efficient manner. So if we were to train two classifiers for men and women, we could try to minimize the loss over men's data, minimize the loss over women's data. We would learn a classifier for men and one for women. Now, how do we make these classifiers adherent to preferred treatment? We can just drop in those formalizations of preferred treatment that we had, that men get more benefits from their classifier than they get from women, and the same condition for women. And these benefits are essentially the probabilities that I noted before. So we can just change our optimization problem. We can minimize the loss and put in these probability conditions. However, it turns out that for many convex loss functions like SVM, even though the loss is convex, the probabilities are actually non-convex. And additionally, they can actually have many saddle points, which makes the optimization pretty hard. So what we'll try to do is we'll try to replace these probabilities with this approximation. So we'll approximate these probabilities using this ramp function. And essentially, this ramp function gives a non-negative output when the point was going to get classified as positive. Otherwise, it gives a 0 output. So we can change our optimization problem like this. We are minimizing the loss, and we are trying to make sure that these ramp approximations follow these constraints. And these constraints are essentially approximations of the original probabilities that we wanted to work with. And since both of the sides of the inequality here are convex, we have a disciplined convex concave program here, and such programs can actually be approximated efficiently. So that's nice. Good. So how do we train a preferred impact classifier? Again, we'll assume we are given two classifiers, two parity impact classifiers, one for men and one for women. So we can do the same thing here. We try to minimize the loss, and we put the ramp approximations of the probabilities that we wanted to work with. And again, this is a disciplined convex concave program, and we can optimize these programs efficiently. Okay, now I'll quickly try to show you a case study that we did on New York police data set. And here we'll just try to answer two questions. The first question we'll answer is, are these preferential fairness constraints that we looked at, are they actually effective? And secondly, we'll try to see, does preferential fairness actually lead to any accuracy gains over parity fairness? So we'll be looking at the New York police data set. So we'll have two sensitive feature groups here, African Americans and whites. We'll have two classes. The non-beneficial class is that a pedestrian will be stopped by police under suspicion of possessing a weapon, and the beneficial outcome is that they will not be stopped. So one thing I would like to point out is that it's a bit of a toy classification task. I'm not sure that somebody is using this data set to build such a classification task. We just got this data from NYPD website, and we tried to work with it. Okay, so the first thing that we did was we trained two classifiers. These are the group conditional classifiers. They're trying to maximize accuracy for both African Americans and whites. This classifier has around a 74% accuracy. That's not bad. What we see is that African Americans, when they use their own classifier, 67% of them get beneficial outcome. However, if they insisted on using classifier for whites, 34% of them would get beneficial outcomes. So there is no incentive for them to change their group. On the other hand, whites using their own classifier get 12% of them get beneficial outcomes. And if they wanted to use the classifier for African Americans, 22% of them would get beneficial outcomes. So whites do have an incentive to change their group. And another thing is that the beneficial outcomes here are actually pretty dissimilar. So next we trained a parity fair classifier. So this is a classifier that adheres to both parity treatment and parity impact. The group benefits for both groups are the same, and neither of the groups has any incentive to change their group, because this is just one classifier for both the groups. However, we see that this leads to a pretty large drop in terms of accuracy. So finally, we trained a classifier that adheres to both notions of preferred fairness. So what we see here is both the groups, they are getting more beneficial outcome than they were getting under parity fair classifier, and neither of the groups has any incentive to change their group. They get more benefits by using their own classifier. And also the accuracy drop is not as big as parity fairness. So what we saw is
a single classifier. The preferred fairness classifier is one classifier.
So preferred fairness classifier, we are training two classifiers. Yes, yes. So one for African Americans, one for whites. So yes, the constraints do seem to work. Each group prefers their own outcome of what they're getting. And yes, there is a smaller loss in accuracy if we use preferred fairness notions as compared to parity fairness. So just to sum up, so here I introduced two preference-based fairness notions. And what we saw is that under these notions, each group prefers to pose as itself, and each group gets more beneficial outcomes than they were getting under parity impact. And we also saw that these preference-based fairness notions actually lead to more accurate solutions. With that, I'll be very happy to take any questions.